So today what I want to look at are rational functions and the asymptotes, and really the asymptotes are the keys to graphing and understanding rational functions. Okay? We have looked at the parent function for a rational function already. We have f of x equals 1 over x. And we mentioned the asymptotes there, okay? What was the vertical asymptote? Well, I guess before we even start that, what is an asymptote in general?
It's a line that approaches but never touches.
Okay, it's this line that our graph is going to approach. The value will approach this value, but it will never actually cross that line. Okay? Now, in the case of our f of x, we said it's a vertical asymptote. That's a value that x will never be allowed to actually equal. All right? So the vertical asymptote is going to be at what line? X equals 0. Good. X equals 0. Okay. And our horizontal asymptote, you've got to think in terms of, okay, what value will our y-coordinate approach but never actually equal? Okay? And what will that be in this case? Very good. It's y equals 0. And particularly here, you have to think in terms of like on either end. Okay? Look at it as x gets really, really, really big or really, really, really small, what's our value going to approach? All right? And if you think about our graph, this makes sense. Okay? Our graph hit the point 1, 1, and it looks like this. Okay? We're approaching y equals 0, but never actually touching it. As we go to the left, we're approaching the y-axis, x equals 0, but we never actually touch it. And then we have this other half over here at -1, -1, and it's going to approach, again, x equals 0 from the left side, but never touch it. And it's going to approach y equals 0 from the bottom, but never actually touch it. Okay? So those are our asymptotes that we have are going to be x equals 0 for the vertical asymptote, and in this case, y equals 0 for the horizontal asymptote. Okay? Yes?
If it was -1 over x, it would just be, the graph would be in coordinate 2 and 4.
That's correct. Yeah, -1 over x would simply be a reflection across the x-axis. So that actually would not impact our asymptotes at all. Okay? So let's take a quick look at these. We have, let f be a rational function. Okay? And you'll notice here it says we have these two functions. We called them n and d because we have a numerator and a denominator. Okay? So n of x is some kind of a polynomial, and d of x is some kind of a polynomial as well. And it says n of x and d of x have no common factors. All right? That's one thing that people sometimes overlook here, that to apply these rules here, they have to have no common factors. Now we'll look in a minute at what happens if they do have common factors. We got to handle those first before we apply these rules. Okay? But let's take a look at it. Okay, it says the graph of f has vertical asymptotes at the zeros of the denominator. Okay? In other words, what's going to make the denominator 0? That's what our vertical asymptotes will be. Okay? Then we have, number 2, the graph of f has at most one horizontal asymptote determined by comparing the degrees of your numerator and denominator. Okay? So let's look at this rule here, and then we're just going to work through a few examples. I think it'll make sense here. Okay? First of all, notice that the lowercase n, if you look up here, lowercase n is the degree of the numerator. Okay? The lowercase m is the degree of your denominator. Alright? So just make sure that you notice that the degree of the numerator, the degree of the denominator. So what this is saying for part A here is that if the degree of your numerator is smaller than the degree of the denominator, then the graph of f has line y equals 0 as a horizontal asymptote. Okay? So the line y equals 0. If the numerator's degree is smaller, then you have y equals 0. Okay? Part B. If the degrees are equal, then your horizontal asymptote is this ratio right here. Y equals this ratio. Can someone put this into their own words?
It's the numerator coefficient over the denominator coefficient.
Okay, look at your leading coefficients. It's the ratio of the leading coefficients. Okay? A sub n was your leading coefficient in your numerator. B sub m is the leading coefficient in your denominator. So it's going to be the ratio of those two coefficients. And then finally C, if n is greater than m, in other words, if the degree in the top is greater than the degree in the bottom, you will have no horizontal asymptotes. Okay? Now, there's a nice way to remember A and C. Okay, and if you had Miss Skokin, you have probably heard this before, okay? Bobo Botten. Alright? This is a really easy way. Honestly, I never even heard of this until a couple years ago when I started, and either she or some of her students mentioned it to me. I thought it was a great way to remember it. What this says is bigger on bottom, 0. Okay, so think of the second O as a 0. Alright? And that's part A here. The denominator of the bottom is bigger. So bigger on bottom, y equals 0 is your asymptote. Okay? And part C here, we can remember with this bottom. Bigger on top, there are none. Okay? So, bigger on bottom, 0. Bigger on top, none. Okay? So let's try a couple here. Okay. Here I have this function f of x equals 2x over 3x squared plus 1. So since we've got it here already, what are our horizontal asymptotes going to be? Let's apply the rule we just learned here. Okay, it's bigger on the bottom. We have an x squared as opposed to an x to the first. So bigger on the bottom. That means y equals 0 is our horizontal asymptote. Okay? By the way, it doesn't just have to be like 1 less. We could have a 2x to the first and an x to the fifth. It doesn't matter how much bigger it is. Just if it's bigger at all, we know it's y equals 0. Okay? Let's think about our domain. Our domain. Notice here we have 3x squared plus 1 in our denominator. So, the domain for this whole function is going to be all real numbers except for what would make our denominator 0, right? So what makes our denominator 0?
The square root of minus 1 over 3.
The square root of minus 1 over 3, right?
Yeah.
Is that a real number?
No.
No? So we could say that our domain is
All real numbers.
all real numbers, okay? We would just say that our domain is all real numbers. Okay? So X is an element of the real numbers. So as a result, what are our vertical asymptotes?
0.
You don't have them.
We don't have any. There are none. Okay? You can't graph the imaginary numbers on our XY plane, so there are no vertical asymptotes. Yes?
You also could have said 3x squared plus 1 equals 0, and it would be like negative rational one, which is imaginary numbers.
Yeah. If you're not sure, set that equal to 0, solve it, plus or minus the square root of negative 1/3, and then you see, oh, that's a complex number, so it's not going to affect our graph. Okay?
Could you say
All right, let's look at a different one here. We have here f of x equals 2x squared over x squared plus 1. Or minus 1, I should say. Minus 1. So, let's look at our horizontal asymptotes. Okay, y equals, notice these are the same. It's squared, this is squared, so our degrees are equal. So good, Rachel, it's y equals 2 because it's y equals 2 over 1. Our leading coefficients are 2 and 1. So we just have y equals 2 for our horizontal asymptote. Question?
Never mind, I understand.
Okay. Now, how about a domain here?
X doesn't equal
X cannot be 1. Anything else? What would make our denominator 0 here? We got an x squared, so there should be 2 things, right? What? Minus 1, good. So plus or minus 1. X cannot be plus or minus 1. So, what's a vertical asymptote? Right?
Square root of 1 half.
Plus or
Square root of 1.
Square root of 1.
Yeah.
Okay.
Plus or minus square root of 1.
Alright, so that's just 1, right?
Yeah.
What were you saying, hon?
That's what
Okay. So remember, if you're giving an asymptote, let's give an equation. Alright? So what would the equation of one of our asymptotes be?
X equals 1.
Good. X equals 1 is one of our asymptotes. And x equals negative 1 would be another asymptote. Okay? Now, the reason why we identify this is so that we can sketch these. Okay? Our goal is to sketch these. So, when we're sketching them, the first thing that we ought to be doing, okay, is, let's see here. First thing that we ought to do is sketch our asymptotes, all right? So I know I have a horizontal asymptote at y equals 2. So there's a horizontal asymptote right there. Okay? I also know I have vertical asymptotes at 1, x equals 1. And I have another one at x equals negative 1. Okay? Now, I have a question here. How are we going to figure out the rest of our graph? Like, we've got the asymptotes, that's nice, so how in the world are we going to graph this thing?
Plug in a number.
Yeah, you can always plug in some numbers, right? What's the easiest point to find on a graph?
1.
1
0.
0.
0.
Yeah, the y-intercept. If you plug in 0, what do we get? 0. Good. So I know 0, 0 works, okay? We can't plug in 1 because those are on asymptotes, right? So here's where understanding a little bit of how these rational functions work goes. If I'm down here and I don't have any multiplicity in when I found my domain or my asymptotes or anything, this is how this is going to work, okay? This is going to approach both of the vertical asymptotes, okay? And as long as I did not have any multiplicity when I was finding that 1 and negative 1, it's going to jump. Notice how it's going, we'll look at positive 1 first. Notice how it's going down to negative infinity as it approaches positive 1. On the other side of it, it's going to jump up to positive infinity. And then what's it going to do as we go to the right? It's going to approach. It's going to approach 2, right? Here's our horizontal asymptote. What does it do? It approaches it. Okay? Yes, Matthew?
So how do you know that the line is above the horizontal asymptote, not below it?
Well, again, this is one thing that just as you do them, you recognize this pattern. As long as there is not a multiplicity when you got that asymptote, you'll have this jump from negative infinity to positive infinity. If you're not sure, plug in x equals 2. You know? If I plug in x equals 2, I get 8 on the top and I get 4 minus 1, so I get 3 on the bottom. So I know I have the point 2 8/3, right? So here's the point 2 8/3. That's 2 2/3, which is bigger than 2, obviously. Okay? So if I try that, if I try a point, that'll tell me whether I'm above the asymptote or below it. Okay? That's an excellent question. So you can look for patterns, but if you're ever not sure, don't forget how we started graphing way back in 6th or 7th grade, you know? Just plugging values in and finding points. Okay? Sometimes it's those easy things that trip us up. Now, since negative 1 did not have any multiplicity either, I'm going to have that same jump again. If I wanted, I could plug in a negative value, okay, or a negative 2, but I'm going to use that jump here to actually see that it's going to start way up there and then approach y equals 2 from the top. Okay? So that's what that graph would look like. Okay? Pretty cool, huh? Yes?
Is there a way to see like how many lines that you're gonna have? Like if you add up maybe the exponents, does it tell you like the number of lines?
Is there a way to see how many what you'll have?
How many graphs?
Oh, how many different parts of it will be? Basically, every vertical asymptote is going to split it up into a separate piece. You know. So, we asked this question here earlier, what's going to happen if we do have some common factors? All right? And the answer that, first of all, is that we need to cancel those out before we do anything else. Okay? And that's where we get to asymptotes versus wholes. Okay? Those common factors are what give us wholes in our graph. Okay? Because if you think about it, if I had the line, let's ignore this this function for a second. If I had a line y equals 2x plus 5, okay? That's just a line. However, let's say I multiplied this by some value of 1, and I happen to make the 1 x minus 3 over x minus 3. Well, I just created a value that x is not allowed to equal in this function. X is not allowed to be 3. However, if I cancel that out, I see, wait, I still just have a line. Okay? So what ends up happening is when I graph this thing, I still have a line. The difference is, right here at 3, I just have this hole. Okay? The common factors just take an original graph and they just poke holes in them. Okay? So how do I know what point this is? It's 3 what?
Calculator.
Well, you gotta know what to put in your calculator.
Plug it into the opposite side of f(x) and then.
Okay. So if I plug in 3 to my original function, I'm gonna get 0 over 0, right? So what do I have to plug it into?
11.
Wait, how are you getting 11, hon?
Probably into y equals to x plus 5.
Yes, plug it into what's left over after you cancel it out. Okay? Because that's the point we would have hit if the hole hadn't been there, right? So I started with the simple one with a line here on purpose because I want you to understand the concept. So let's look at one with a rational function. F of x equals x squared plus x minus 2 over x squared minus x minus 6. Alright, so let's work our way through this one. Let's start with the easiest part, I think. We've got it here. What's the horizontal asymptote?
0 at y equals 1.
Yeah, we have the same coefficients, right? 2 and 2. And the leading coefficients are 1 and 1. So we have y equals 1 over 1. Or just y equals 1. Yeah.
How do you find the domain?
Good question. How do we find the domain?
So if you find the zeros and then on the denominator.
Denominator. There we go. Okay. So let's think about this. How are we going to find zeros in our denominator?
Set equal to 0.
Factor. Okay. And think about what would make it equal to 0. So if I factor my denominator, what do I get here?
X minus 3, x plus 2.
There we go. X minus 3 and x plus 2. And hey, while we're at it, we might as well factor the numerator too. What does that factor into?
All they're shooting is 1.
X plus 2.
X
Good. X plus 2, x minus 1. Alright? So, question, before we do anything else, what's our domain?
All real numbers.
X doesn't equal 3 and negative 2.
Why can't it equal 3 or negative 2? That'd give us a 0 in our denominator, right? But we're not allowed to have zeros in our denominator. Okay? So, here's the question. I have two numbers that are zeros of my original function. Technically speaking, though, my original function isn't the rational that we were talking about because it already had, it has some common factors here. Okay? So what do the common factors give us?
0 plus 2 gets rid of both.
Yes, but that doesn't answer my question. What do the common factors give us? Holes. Alright? So, when we cancel this out, we're identifying the hole. So the hole occurs where?
Negative.
At negative 2 something. Alright? So now I have the function x minus 1 over x minus 3. Okay?
So you plug in negative 2.
So there we go. We've got to plug in that negative 2
Why negative 2? Thank you. Okay.
to find our hole, to find the y coordinate of our hole. Where would we have hit if we hadn't had that
0.
common factor there? Okay? So we get negative 2 minus 1 over negative 2 minus 3. Okay, notice I'm plugging the negative 2 into that leftover part. So I get a negative 3 over negative 5. So I get 3/5. And it's not uncommon for these to just be kind of odd points there. All right?
Wait, if the hole is on the asymptote, does that mean that the line goes through the asymptote, but it doesn't like touch the asymptote?
Nor.
Well, no. Notice here, negative 2 does not give us an asymptote. Negative 2 gives us a hole. What's our vertical asymptote here?
3 and negative.
It's got to be a line, right?
X equals 3.
X equals 3. So here's kind of a rule here, guys. When you identify your domain, those values are going to give you either asymptotes or holes. You can't have one value that gives you both. Okay? If it cancels out, that means it was a hole. If it's left over in your final rational function, then that means it's an asymptote. Okay? So, identify your domain before you reduce anything. Then look to see if something cancels. If it does, that element of the domain gives you a hole. If it's left over, that part of the domain gives us a vertical asymptote. Okay? And then once again, we can graph this. One thing that'll help us is identifying a zero. Are there any zeros of this function?
Yeah.
Where?
At 3 and negative.
No, zeros of the rational function. What would make this thing equal 0?
30.
No, 3's not in our domain, right? That would make it undefined.
So no.
In order for a fraction to equal 0, what has to be 0?
So 1.
The numerator has to be 0, right?
Oh.
You have to have 0 over something, okay? So 1 minus 1 would be 0. So that means I have a 0 at the point 1, 0. Identifying that makes it helpful, makes it easier to graph, okay? Gives us a point to graph. So here, I have a 0 at the point 1, 0. I have a hole at the point negative 2, 3/5. I'm going to put that right there. I have a horizontal asymptote at 1. Okay? And I have a vertical asymptote at x equals 3. All right. So, check out what this looks like. We must be in this bottom left side. We have 2 points that are on this bottom left side here. We must be approaching the horizontal asymptote there. We hit the 0, and then we're approaching the vertical asymptote here. Okay?
I have a question. How did you find your 0?
I just made the numerator 0. X minus 1 equals 0 when x equals 1.
Why wouldn't you find the denominator?
Well, we already know the denominator is 0 at 3. That's how we got our domain. Okay? But that would make our function undefined. It won't make our function equal 0.
Would you equal the whole thing to 0?
Yeah. But if you have a fraction, the only way your fraction can equal 0 is if your numerator is 0. Okay? Now, remember a rational function has 2 parts. Okay? And they're diagonal from each other, typically. Okay? So our other half of it is going to be up here. It's going to be approaching the asymptotes up there. Okay? So, we're applying a lot of stuff that we've learned already, finding zeros and all that stuff. This is just one application of all of that. Yes?
So your asymptote zeros cannot be the same.
Your asymptotes, holes, and zeros. Theoretically, you could have a zero that's the same if you had like a x plus 2 squared in the numerator, so only one of them canceled. But actually, then it would be the whole would be a zero.
So no.
So yeah, it wouldn't work. So yeah, you're right. They can't all be the same.
Thank you, sir.
All right, so I want to include one more example here of graphing with a rational function. First thing we should do here, we can identify horizontal asymptotes. This is a 2, it's a 3, so bigger on bottom, y equals 0. And then we want to identify the domains. Let's factor our denominator. Factor out an x, and then you have x squared plus minus 16, so that factors into x plus 4x minus 4. We'll get to our numerator in a sec, but right now we can say that our domain is that x cannot be 0, -4, or +4. So that means those three values are either going to give us vertical asymptotes or holes. So to figure out what's what, we're going to factor our numerator. That's x plus 4 times x minus 3. And you'll notice here, the x plus 4s will cancel out. That means that -4 gives us a hole. And our vertical asymptotes are going to be x equals 0 and x equals 4. Okay? So the one that cancels, this one, gives us a hole. The other two give us asymptotes. So now we look at what's left over. X minus 3 over x times x minus 4. To figure out the y coordinate of our hole, we're going to plug in -4 to what's left. So we get -4 minus 3 over -4 times -4 minus 4. So that's a -7 over -4 times -8 is a +32. So that's a -7 32nds. That's our hole. So I'm going to actually put that on here. -4, -7 32nds. So right about here. I should make that a hole. Let's make that a hole right there. And then the zeros are all going to make the numerator 0. So x minus 3 is 0. So that's x equals 3. So we know we have the point 3, 0 on our graph. Okay? So let's look at everything we've got. Our horizontal asymptotes. We have one at y equals, y equals 0. Okay. We also have vertical asymptotes. So actually, here's our horizontal asymptote right here. We'll get to how we can have a 0 on our horizontal asymptote in a second. We also have x equals 0 as a vertical asymptote, and then also x equals 4. Now, one thing to understand about horizontal asymptotes that make them a little different than vertical asymptotes is that the horizontal asymptotes are lines that we will not cross on either end. All right, I mentioned in class, you look at as x gets really, really big or x gets really, really small. Okay, so that is how we actually get a situation like this where we're going to approach 0 over here. Here's our asymptote. It's going to approach, just approach this value there. So that's part of it. Then we jump up to positive infinity. And this. And we can hit the horizontal asymptote in the middle, but then it's going to jump up and we approach the horizontal asymptote there. Okay, so you see this asymptotic behavior, we call it, on either end. All right, here it's approaching the horizontal asymptote. On this end, it's approaching the horizontal asymptote. It is possible, however, to cross the asymptote in the middle. All right, so this one's a little bit odd in that sense, but again, all the principles still apply.